All right, let's get started here. Hello, everybody. Hopefully you're doing well. Welcome to another lecture, another day. We had a tornado warning in my area recently, and now it was crazy for a while. Overcast, very windy. Now it's like bright and sunny out. I don't know what's going on. Hopefully you're all doing okay. We are going to continue this whole Cal 2 thing. But before that, I just want to make some announcements. So you guys have probably seen the emails, but just in case, because it's very important. So one, the math department finally has a plan for final exams, even though they haven't revealed all the details yet. So we do know that the final, AJ's coming in. So we do know that the final will be online, and that's for sure. And this will continue to the summer, and that's for sure. I'm not sure about the fall, what's going to happen, but we don't have to worry about that right now. So the final exam will be online. And another important thing is that it will be through Blackboard. So even though we haven't been using Blackboard in this class, you need to make sure that you know how to log into Blackboard under your own student account. So start working on that right now. Make sure that you can actually get into Blackboard. You can look around, your account is fine, and everything will be good to go by that time. So I don't remember the exact final date. So the final is going to be 3-4 weeks away. I don't remember. That's the first thing. So final exam will be online. It will be through Blackboard, which, by the way, kind of tells me that the format is probably going to be very different than it usually is. I would assume that if it's going to be through Blackboard, that it will be, the format will be more like short answer and or multiple choice, sort of fill in the blank kind of thing, something that you can answer really quickly. So that is the first thing. So that might be a little bit of a change. So yeah, that will be the final. All finals are departmental. So I also mentioned that in an email. So just to make sure that everyone is aware of that. So you guys were always going to take a departmental final as well. You guys are always going to take a departmental final because you guys start at 4 p.m. My other class wasn't though, but now they're also doing the same final. So we're doing a departmental final. It will be sent out using Blackboard. Yeah, so for my test, yes. I don't know if you necessarily need a laptop camera. It will probably also work with a phone camera. I'll get to my test pretty soon. I'll talk about those in a bit. But I do want to make sure that you know about the final for the class. It's not written by me. It is going to be online through Blackboard. It is going to be at the times, one of the 2 times I sent you. So I sent you 2 possible date and times for the final. It's going to be one of those. So use this time to check that you don't have conflicts and to check that your Blackboard actually works under the correct student account. Maybe this doesn't apply to any of you, but as a faculty and staff member of City College, I have several Blackboard accounts. So, which if anyone out there also is in that boat, make sure you're logged into the right one, the one that's connected to the student ID that you registered this class for. So that's probably nobody, but just in case. So the final departmental through Blackboard, it'll be on either of the dates that I sent you in an email earlier. In terms of my tests, so remember our test is the 29th or 30th. It's next week, Thursday. So it's 1 week from the Thursday coming. So next week, Thursday, which is the 30th, is going to be our test. And then we'll have another one about 2 weeks after that. So ours is going to be Thursday. Okay, so now originally the solution that I had in mind, which I really like, isn't going to work out, but we got a close approximation of it to work out. We're working out the technical details with the platform that I want to use, which is Top Hat. So I will definitely have to be sending you more details on that, and I have to rewrite the format that I use so that it will fit on this thing, because I think I'm gonna have to upload everything as pictures, whereas I actually typed it up in LaTeX. So I'm gonna have to change that. So your mock test is probably gonna take a little bit longer. I'm going to upload it tonight. So for test 1, as I mentioned, it's everything up to series. To be a little bit more specific, I asked questions on just you computing integrals. So just here's a set of integrals, integrate them, with one of them being a definite integral. Then there's numerical integration, which means like Simpson's rule, trapezoid rule, that sort of thing. There's a question where you have to do a couple improper integrals. Then there are questions where you just have to tell me whether or not a series converges absolutely, conditionally, or diverges. Then there's a question that asks you to find the radius of convergence and interval of convergence of a power series. Then we have using Taylor-Maclaurin series to compute an integral, and then a problem on just finding the Taylor-Maclaurin series of a function. So yeah, I actually do want to run the mock test on top. So I'll actually give you guys 2 mock tests. So I'm going to give you one, which you're going to do on paper just to get used to the topics. And then just to make sure that everything runs smoothly on Thursday, I do want us to do like a trial run earlier in that week, like Monday or Tuesday of next week, to make sure that by the time Thursday comes around, everyone is good. I probably won't give you the answers right away, so I don't know. I might do the solutions for one of them. The others you'd have to like ask me during office hours or just ask me. But that being said, I did teach you guys how to use like Wolfram Alpha and all that stuff. So technically, even if I don't tell you what the answers are, you should be able to find them on your own. But given all the setup I'm doing, I don't know how much time I'll have to actually write up all the solutions and scan all that stuff in. And so that is sort of the nitty gritty here. So those 2 things I wanted to say. I don't think there's any other announcements for the time being. I think that's it. So now you know about the final, now you know a little bit more about your test, and I'll be posting a couple mock exams. One just straight up paper, just do it in your own time, and then another one next week where I actually want you guys to take a crack at using the platform Top Hat. Okay, so yes, the mock test is going to be similar to exam. Wouldn't that be crazy? Like I give you guys a mock test and then the actual test looks nothing like. Yeah, one day I'll do that. It won't be today. It won't be this week. So one day we'll see. Wonder if anyone would notice. I've actually had students in the past where I'm teaching several different classes, and somehow they got the dates mixed up and they show up for the final of another class, and they take the final and they don't even realize that it's not the right class. Like, yeah, some people are so lost. I don't know, but yeah, it will be similar. That being said, let's actually jump into it. All right, so let me share the screen here. Okay, a couple more people trickling in. All right, so this is what we were doing last time. And as always, I am going to turn off my video to sort of minimize the amount of glitchiness that can happen. So now you'll just listen to my smooth voice tell you about mathematics and try to stay awake. Okay, so last time we looked at vectors. Introduction to vectors. What are they? How we can draw them? How we can write them down mathematically, which is as components, like coordinates with straight arrow bars. You can look at these coordinates as telling you how far you move in each direction, like the x direction and the y direction, or the x and the y and the z direction. Specifically when your vector is a position vector. So position vectors in general, we care about their magnitude and direction. They can be anywhere in space, and we'll consider them to be the same vector as long as their magnitude and direction are the same. If I fix a vector to the origin specifically, it is then called a position vector, because that vector is actually going to hit the coordinate. So that vector is actually going to hit the coordinate that looks like A1, A2. Even though it's not a coordinate, it just tells you it moves to the right by A1 and then moves up by A2 to hit that, and then that's a position vector. Okay, so we have that. We also saw that we can create a vector that connects 2 points. That's going to be important in a few sections. We know how to find the magnitude of a vector. And we know about some properties of some operations on vectors. So we can add them together, and we know that we can multiply vectors by scalars. Notice that there's no operation of multiplication between two vectors in the sense that you know about multiplication and division from before. Such an operation doesn't exist with vectors, but we are going to do operations on vectors that we call products, but they're not going to be like something that you can divide away. So I want you to understand that multiplication, strictly speaking, for vectors isn't a thing. There are variations on it. So we have scalar multiplication. I can multiply a vector by a scalar. A scalar is just a quantity that has no direction. It only has magnitude. For us, the scalars will just be real numbers, positive or negative or zero. Another thing, geometrically, when we add vectors together, we get resultant vectors, and you just kind of put the vectors tail to head, and then go from the starting point to the ending point. Multiplying a vector by a scalar actually scales it. It's one of the reasons why we call the numbers scalars in this context. So if I multiply a vector by 2, it actually stretches it by 2 and maintains its direction. If I multiply a vector by a negative scalar, it flips the direction directly around. Nonetheless, all vectors of this form are considered parallel. Vectors are parallel if one is a constant multiple of the other. To subtract vectors, that is an operation that is defined. We just define that as adding the negative of one vector. So you flip it the other way, and then you add that to the tail, and you can get the negatives. Okay. These are the properties that vectors have. So algebraically speaking, when you're doing math and calculations with them, these actually work. The zero vector is a guy we also spoke about last time, very weird guy. He does operate kind of like zeros with numbers. If you add him to anything, it makes no difference, and so on. But strictly speaking, the zero vector has no direction and all directions all at the same time. And by the time I finish covering the next 2 sections, that will be more clear as to why we can say that. And then we just did a few computations here, and that's where we wrapped up with the last time. Now we're going to pick up. So we're going to want to finish up this section. There's a few more things I want to tell you about vectors, and we're going to go into the meat and potatoes of today's lecture, which I think should be very interesting. And the next lecture is going to be very interesting. Normally when we're going to be talking about the dot product today, that's the main course. And Thursday, we're going to talk about something called the cross product. And there is a way to present these guys where it's just like a definition. Here's the math definition, and it's very dry and just, okay, that's the definition, let's use it. But I do want to actually provide some sort of motivation in the lectures. So I'm not just going to tell you what a dot product is and what a cross product is. I'm going to sort of tell you where do they come from, what considerations led to their invention, and kind of why they're important. We're going to kind of start to build up to it from that road. So that's where we're going. Before we get there, though, I want to tell you about a new notation for vectors, the Ijk notation. And I also want to talk about the idea of something called a unit vector. Once we have those guys, we'll be able to move forward. Okay, so let's talk about, these guys are called basis vectors. and they're called, I'm going to introduce things called the standard basis vectors. Okay, so these guys if we're doing Rn, the Euclidean n space, n-dimensional space, where we kind of think of it in terms of rectangular coordinates, these guys have the following form. They have all coordinates 0 except one coordinate, where in that position is a 1. These guys are the E sub I, and E sub I has the I tells you the location of the 1. So if we're in 4D space, then E sub 4 would be the vector that has 1 in the 4th position. E sub 2 would be the vector that has 1 in the 2nd position, and so on. But there are 4 coordinates in general. So these guys are that. This, though, however, is more like the notation that's used in abstract mathematics. So most people, engineers and the like, are never going to really use that notation. In R2 and R3, we give these guys different names. We call them the I vector and the J vector in R2. We also call them the I, J, and K vectors in R3. Some people refer to these as I hat, J hat, K hat. Basically what these guys are, these are vectors that run along the axes and they have a length of 1. Oh, there I go again. There I go again. Right? So you can imagine the I vector starts at the origin. It runs along the X. And it has a length 1. That is your vector I. Then we have another vector that runs along the Y, right? Runs right along the axis, starting at the origin. That guy also has length 1. That guy we call J. And then there is a third vector, starts at the origin, runs along the Z. That guy we call K. Now remember, to indicate vectors, we put little arrows over them. So it's I hat, K hat, J hat. Okay? So these are what they're called. And basically what the I is in R3, your I is the guy that has the first coordinate 1, all the others 0. Your J is the guy that has the second coordinate 1, all the others 0. Your K is the guy that has the last coordinate 1, all others 0. Okay, so those are I hat, J hat, K hat. Okay, these are called the standard basis vectors, or everyone would know them as I, J, K. Notation-wise, they provide another notation for vectors. So this leads to the IJK notation. Given a vector, let's say I have a vector A, which is A1, comma, A2, comma, A3. Notice by the rules, properties of vectors that we mentioned last time, I'm not going to go over them. I can express this as A1 times 1, 0, 0, plus A2 times 0, 1, 0, plus A3 times 0, 0, 1. Scalar multiplication says I can multiply this in, the other two are 0, multiply this in, the other two are 0, multiply this in, the other two are 0. When I add them together, I just add corresponding components. It builds up to that. But that basically means that I can have I, A1 times I, A2 times J, and A3 times K. So this here is the IJK notation of the vector. Right? This guy here has several names, but we normally call it the component notation. Although you can talk about the IJK as a component notation as well. We don't really call these anything. So that's it. So for example, the vector 1, 2, minus 3, I can write that guy as I plus 2j minus 3k. Now, one thing I do want you to be aware of, you are not allowed to mix notations. Do not mix the notations. So let's put an exclamation here. So if you write something like I, comma, 2j, comma, minus 3k, what are you doing? Wrong, right? Either use ijk and additions and subtractions of the terms, or you use the square, the sharp brackets and coordinate form. Do not mix them together. Okay, this is a very different object. It's closer to something that's a tensor rather than a vector. So it's a very different object. It does not mean the same thing. Do not mix the notation. Either use ijk or use this. Do not use both. You do need to know both of them because a problem might be stated to you in either version. Personally, I will write this one more just because it's easier to write, but it's no more correct than this one. So whether a vector is given to you in this form or that form, you should be able to surmise that, okay, the x coordinate is this, the y coordinate is that, the k coordinate is that. No, you do not think of them as I is 1 and j is 2 and k is 3. That's not what they are. I, j, and k are these vectors specifically. They will always be these vectors. Right? But we can multiply vectors by a number, and when we add them together, we can create another vector. Right? So this here is called a linear combination of the vectors I, j, k, and that's kind of where the term basis vectors come from. This is called a linear combination. Any vector in R3 can be expressed. Hold on. Let's move this chat box out of the way here. As a linear combination of I, j, k. Okay. This is one of the conditions that creates something that we call a basis, but that's a linear algebra phrase, and that's why they're called basis vectors. But yeah, that's basically it, ijk. So now we know that. Another thing that we are going to want to talk about, making sure we all know this, is the idea of a unit vector. Now, don't let the new phrase scare you. It's very simple. A unit vector is just a vector of length 1. In fact, ijk are all unit vectors. These guys are unit vectors. They have length 1. Magnitude is 1 here. So if you have a vector and its magnitude is 1, it's called a unit vector. Now, one thing that's important is that given some vector pointing in an arbitrary direction, we would often want to know how to find the unit vector pointing in that direction. So how we'd go about doing that? Well, we'd scale it. So if we have a vector pointing in some direction, all I have to do is multiply by 1 over the magnitude of that vector, and its magnitude is going to end up being 1 after doing that. So for example, here is my, let's do an example. Here is 2 minus 1, 3. So if I wanted a unit vector in the same direction as, oh, it says find 2 unit vectors that are parallel to 2 minus 1, 3. This thing is misbehaving again. Sometimes it does this. Hold on. Lots of things are glitchy today. Okay, let's see here. Okay, so let's find a unit vector. So A is the vector 2, 1, 3. If I wanted to find a unit vector in the same direction, I would just want to take A divided by the magnitude of A. And that's always how you create a unit vector in the same direction as some other vector. So for example, in this case, it would be 2 minus 1, 3 divided by the magnitude of 2 minus 1, 3, which now we know that that is the square root of the sum of the squares of the components. So that is 4 plus 1 plus 9. Right, so that's radical 14. So this is 2 minus 1, 3 over radical 14. Or in other words, you can write it as 2 over radical 14, comma, minus 1 over radical 14, comma, 3 over radical 14. And this guy is a unit vector. Same direction as A. Now it says find two of them, and we want it to be parallel, which means it needs to be a scalar multiple. The other is actually minus u. Right, that literally flips the vector backwards. I have to multiply it by a 1 because I don't want to scale it. I want the length to be maintained. So that's the other one. Let's just throw that out there. So here what we have is we have some vector A. This is the vector A. And in fact, its length is the square root of 14. And what we've just found is a vector u. That's pointing in the same direction as A. And that has length 1. And we can talk about the vector minus u is just the guy that's pointing in the opposite direction. And that also has length 1. Okay. So that's it. So Ijk notation, we can write any vector as the x component times the I hat plus the j component times the k hat plus the z component times the k hat. And a vector whose magnitude is 1 is called a unit vector. You can create unit vectors at any point by taking the vector and dividing by the magnitude of that vector. The vector is non-zero. This creates a unit vector that points in the same direction. This is important because there's going to be a lot of mathematical operations that we're going to need to do where we're going to need to, it's going to involve vectors and we're going to care about their direction, but we're going to want the vectors to be unit vectors so that they don't scale other parts of the calculation. We want things to maintain a certain scaling. Of course, multiplying by a scalar of 1 doesn't change your answer. So this is why unit vectors are actually going to be very important. Okay, so hopefully no questions there. Are there any questions there? Or are we good? Boom, now we're moving on to the dot product. Okay, so this is what we're going to spend the rest of our time on today. But first, I do want to talk about the motivation of the dot product, okay? As well as the motivation behind the next section as well. Okay, so we've noticed already that navigating the 3D world has challenges, and we see that a lot of our notations and a lot of the way that we think about things in 3 dimensions actually does not work out as they would in 2 dimensions. Simple examples, like I mentioned here, x equals 1 is a line in 2 dimensions, but it's a plane in 3 dimensions. And say x squared plus y squared equals 1 is a circle in 2 dimensions, but it's actually a cylinder in 3 dimensions. So just writing down our notation, they actually mean something completely different based on the dimensions that we're working in, right? So there are lots of differences. So we have to look at the world in a different way. Now, one of the things that helps us to navigate the 3-dimensional world and worlds in higher dimensions are vectors. So rather than talking about a location in terms of a curve, like x squared plus y squared equals 1 would just identify all locations that are at a distance 1 from the origin, it's better that we identify locations via vectors. So we're going to talk about, okay, we are identifying all the locations in space that are at the tip of this vector projected from the origin. That's a nicer way to actually look at it, and it's a way that generalizes nicely to higher dimensions. Once we find a way to write things down in terms of vectors, then even if you increase the dimensions, the notation can stay exactly the same, and it will actually mean exactly the same thing. So vectors are actually pretty useful, and that's why we needed to talk about vectors. Now, there are going to be other things that are useful. So here's some mathematical object in 3 space. Once you start to talk about, okay, I know how to identify locations in my space. Now we're going to have to know how do we actually get math done in the space? Specifically, we're in calculus class. How do we get calculus done in 3 space? So here's the thing. We need to know what would we need to be able to do calculus in 3 space. And so we start thinking back to Calc 1, how we actually invented all the things that we needed and what we had to accomplish in order to invent these things. So what are the main stars of calculus in Calc 1? Well, the derivative and the integral, of course. What is the derivative? Well, it's a way to find slope. We use limits to find slope. What is the point of a slope? Well, a slope helps us to talk about the direction in which a curve is moving. Is it increasing? Is it decreasing? Going up or going down? It's a measure of direction, right? And now we also know vectors are a measure of direction, but the vector is the guy giving us the location. We'll need another vector to talk about direction. How are these going to interplay on each other? That's going to be an issue. Next thing what we wanted to do is integration. How does integration work? Well, think of a Riemann sum. How do we build up an integral? Well, you're on the XY plane. You decide that you want to integrate along some axis, some interval on the x-axis, for example. So interval between A and B. What did you do? You have to cut it up into subintervals. And then you have to find a way to measure the length of these subintervals. Then you have to multiply that by the output of your function. This gives you the area of the rectangle, and then you get a Riemann sum once you take an infinite number of these rectangles. So there needs to be a way to dissect the world that the independent variable lives in. And then we need to be able to measure the length or magnitude of these dissections. If we cannot do that, we cannot do integration. So what does that mean for us in 3 dimensions? Well, what would our input space be? So if we look at this object here, notice that inputs in 3D will often be the case that we will have, so something like this guy would have an equation looking like z equals some function of x and y, right? In the same way that, say, z equals x squared plus y squared would give you a paraboloid, or x squared plus y squared equals 4 would give you a cylinder. We can often write functions in this form, which means that their x and y's are inputs, which means if in the xy plane, I take a coordinate x comma y, I am going to plug that into z, and I will get an output out here, which is z. And so what you'll realize is that our input space could be some region in the xy plane. So instead of having an interval, we can have some space in the xy plane that's where our inputs are coming from, and our outputs get projected into 3 space. Now we have to worry about, well, if that's our input space, how do we make dissections? How do we set up things like a Riemann sum? Well, you do it like this. You do it in patches. So no longer are you going to just cut up a line into something. You have to cut up a 2-dimensional thing into a bunch of patches, right? So you're going to slice across and like that. And ultimately, these patches are projected into this function. And we kind of essentially do calculus Riemann sums for each of these patches. So the equivalent for us of taking some interval on the x-axis and dicing it up into subintervals, this now becomes the idea of creating patches in 3 space. We now don't care about the lengths of intervals, but rather we care about the area of patches. We have to have some way to measure these patches that we're creating to actually piece together some function that we care about, right? And we can do calculus by these pieces, right? So ultimately, if I take one of these guys, these yellow patches, right? So let's say I look at him here. There are some things I'm going to want to know. First of all, the directions. Oftentimes, direction is going to be in terms of angles. If I know the angles, let's say I have 2 vectors running along the patch. Okay, so let's say I take one of those patches and I have a vector A that's running along this patch, and I have a vector B that's running this way, right? So I can run along the outer edges by vectors. Is there, and of course, remember, in 3 dimensions, vectors are very useful to talk about everything. If I want to know the location from this point to that point, doing it with a vector is going to be useful. How would I find the area of this patch so that I could do something like set up a Riemann sum? These are questions that we're going to want to be able to ask ourselves, right? Now, let's actually talk about that. How would we find the area of this patch? Well, here's one way we can do it. Let's say I have the patch here. What we can do is realize that the patch is actually 2 similar triangles stitched together. So I can take one of those guys. So the length of this part is A, the length of that part is B, and the angle between them is theta. So notice that we now have a triangle, and the area of this area of triangle is equal to half the area of the patch. So now, if we can find the area of such a triangle, we'd be able to figure out the area of the patch. And the area of the triangle is going to be what? So this is where someone chimes in who remembers their high school geometry. If you have a triangle where you know 2 sides and an included angle, how can you find the area?
Law of cosine?
No, law of cosine doesn't help you find area.
SOHCAHTOA and do Pythagorean theorem.
Pythagorean theorem applies to right angles.
Oops.
Yeah.
I know. Hold on.
1/2 base times height, but how do you know the height of this triangle? Okay, so the formula is the following. It's 1/2 times the product of the 2 sides times the sine of the included angle. Half AB sine theta. Okay, so that's how we can find the area. And yes, you cut it perpendicularly here, and then you do actually use Pythagoras' theorem to help you figure out the height, but that's a whole other thing. You can ultimately prove this, which ultimately that means, come again? Well, so ultimately that means that the area of the patch is going to be, well, it's going to be double this. So it's going to be A times the magnitude of vector B times the sine of the angle in between the vectors, right? Now that is an important idea, and that idea is actually used in the cross product. We'll get to that pretty soon. So knowing how to find the area is going to be super important. Why? Because of things like integration. We need to be able to measure our dissections to be able to do an integration. So that leads to this formula. That's how we'd find the area of a patch. Once we can find the angle between 2 vectors running along the edges of the patch, I know how to figure out the area. And that leads us to another problem, doesn't it? How do we figure out the angle between the areas of the patch, right? We'll get back to area in the next section, but for now, what about the angle? If I care about theta, I can do a very similar thing. I can call this vector, say A, call this vector B, and again, I'm considering the triangle here now because I really care about this angle. Now, as drawn here, right? It's not going to matter in the end, but I just want to make sure that you guys know how you're actually looking at this. What is this vector, this black vector here? Can you tell me what that would have to be in terms of the vectors A and B?
Negative B.
Well, negative B would be the vector pointing in this direction. That won't be the same direction.
Mm.
Right? Negative B would just be this blue arrow flipped literally the opposite way. That's pointing in a totally different direction. The black arrow, what is that? It's A minus B, right? So this vector here is going to be the vector A minus B. Run along A, subtract B, and you'll get a vector that goes from here and points in that direction. This is the vector A minus B. So let's call that the vector C, okay? So now we have a triangle where one side is the magnitude of A, another side is the magnitude of B, this side has the magnitude of C, and I know an angle in between these. How can I find the angle? And so that was the answer here. How can I find the angle? Now, someone did mention this earlier, but it was just in the wrong context. You could use law of sines, but law of sines would require you to know about this guy over here. So if I only wanted to use A and B, law of cosines would actually be better. Now, of course, you all remember the law of cosines. I know you do. But just in case, that's what the law of cosines look like. Not that I don't trust you guys or anything. So here's a triangle. Law of the cosine says this is the case. So for us, the equivalent angle here would be the angle C. This equation would tell us how to find C. So in other words, but in the patch above, by the law of cosines, this will be the case. If I take the magnitude of A minus B squared, that is going to give me the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A magnitude of B, cosine the included angle. And I would actually be able to find the cosine of the angle that way, right? So this would be, well, let's do A squared plus B squared minus A minus B squared all over 2AB, right? Then I can take cosine inverse and I can get to the angle, right? So this equation is important. We're actually going to come back to it in a little bit later, but that's how we could figure out the angle between two vectors. We can use this equation to help us out, right? And we'll get back to this in this section. So we're actually going to talk about that. That's going to be important. I'm dissecting patches. I have some concerns. I need to know, how do I measure the area of these patches? How do I measure the angle between the vectors along the patch so I can really know how to describe them using vectors? We've just covered those two guys using high school trigonometry. So to be a little bit cheeky, this is how you're going to use those things in your life. You're going to use the math that you've learned to derive other math. I'm kidding, but it's true though. That is actually true. Like, when am I going to use this in my life? Well, you're going to use it in Calc 3, dude. When am I going to use Calc 3? Well, wait until you get tired and you'll realize eventually, yeah, it's just a ever winding ladder. As time goes on, we just need more math, and we use the old math to develop the new math. Anyway, going off on a tangent. Another direction, you use Calc 3 for Calc 4. Yeah, exactly. Now let's talk about the direction. Direction is going to be important in the sense of like slope. So if I wanted to talk about, what about the angle in which this patch is situated in space? Is there a notion for that? I have this patch hovering in space. Right? So here's 3 space, and I have this little patch. How can we measure how the patch is, I don't know, let's say tilted? Okay. Now, some people might already know the answer to this, especially if you've seen these topics before and you did a lot with vectors. But just for fun, maybe someone tell me a way of talking about direction of this patch. Like, what would you think would be a useful way to talk about the direction of that patch? What is the direction of its slant, right? So just like how in 2D back in Calc 1, I could have a line like y equals 3x plus 4, and we can talk about the slant of that line. We can say the slope of that line is 3. I can measure it with the slope, and everyone would kind of know, oh, so it's tilted, it's steeper than a line that would have slope 2, and so on. How can I measure a patch hovering in 3 space? How do I talk about its direction? Guesses on direction. What do you guys think? See what plane it's parallel to? Okay, that's an idea, but how would you know how the plane is tilted? But I guess to be able to say it's parallel to this plane, you want to be able to say, well, I know the direction of this plane. How would you talk about the direction of a plane then? Which is equivalent to the direction of this patch. You can just think of it as a very small plane, a piece of a plane. Ideas for talking about it. How'd you get basis vectors? Yeah, positive and negative doesn't really make sense. There's a positive direction is very weird in this sense. It's not, we're not in a 2D world where it's like positive is moving to the right and negative is moving to the left. Think vectors. Can you use a vector to describe where this guy's pointing? What vector would describe where this guy's pointing? Pick 2 points in the plane and create a vector. Okay, that seems like a good idea. So you'll just pick a point here, and you can make a vector with it. And is that good enough? No? So that's a problem, right? Using a parallel vector, any parallel vector is going to be an issue. Now, this is the point where we actually need, yeah, don't be sad, Ash. It was actually a good first guess. For someone who doesn't know about this stuff, that would be the first logical guess. But there are issues with, even if I could actually do this, find points in the patch and then actually create a vector, it's still not good enough. To actually show you why it's not good enough, this is why we need in-person lectures sometimes. It's better if I actually just kind of show you. So can you guys see me now?
Yeah.
Okay, cool. So, all right. Here is the plane, right? This is the book. I really like this book, by the way. It's a nice book, very good book. Math majors, you'll probably use this book. Okay, so this is the patch, right? The plane, okay? And here is a vector, right? The tip of my pen is the terminal point of the vector, and the eraser is the tail, right? The initial point. If I have a vector in this book, can I talk about the direction in which the book is slanted? The idea is no, because that vector is also parallel to the book, pointing in a completely different direction. That is the same thing, that is the same thing. pointing this way, the same thing, pointing this way, the same thing. In fact, there would be an infinite number of vectors that are parallel to this book. So if I decide to pick this vector as how I'm going to talk about direction, I could be speaking to a million different people and we'd all have a million different interpretations of what direction I'm pointing in. Not good enough. The fact that there's an arbitrary number of ways, an infinite number of ways, makes it a problem. Being parallel to the plane is not a good way to describe the direction of the plane, right? Which is kind of weird because when we think about describing the direction of a line in 2D, we want to be parallel to the slope to describe the direction. This is no longer true in 3 directions, in 3 dimensions or higher. So, okay, so we don't want to be parallel to the plane. Does that mean we want to not be parallel to the plane? So now, okay, so can I describe the direction of a plane by some vector that's poking out of the plane? And again, there are issues. So for example, let's say I'm going to use a vector that's 30 degrees to the plane, and I'm going to talk about that as being the direction. Now you actually turn out to be in the same issue because this and that are the same, right? Like there are an infinite number of vectors pointing in different directions that are all 30 degrees to this plane. It turns out for every angle that you can poke off this plane, you're going to run up into the same issue, except one angle. Can anyone think of what angle is not going to run into this issue? 90 degrees. A right angle, that is the right angle. The right angle is the, okay, that's 2, okay. Pardon the pun. Okay, the right angle will not have this issue. You see, no matter where I put a vector on this plane, if it's at a right angle, it is considered to be the same vector. Its magnitude and direction are all the same. It's pointing straight up, okay? A vector that meets the plane at a perpendicular angle is how we're going to define its direction. Now, could someone get a different answer? Yes, but there's only one other possible answer, the one that's pointing directly in the opposite direction. And that is parallel. So for all intents and purposes, it's the same vector. If I use a perpendicular vector to describe the direction of a plane, it is uniquely describable in the sense that everyone would know exactly what direction this plane is pointing in, because there's only one direction that's going to be perpendicular. For any other case, there's an infinite number of directions that I can choose, and that makes it a big deal. So being able to find a perpendicular vector is something that's going to be very important to us. So, and this vector, by the way, is called a normal vector, right? I don't know why they call it. I don't think it's any more normal than any other vector, but whatever, it's called a normal vector. So now the question is, okay, so I know what vector I want to find. It's the one that's perpendicular to the plane. Now the question is, how would we find such a vector? The vector to describe the direction is a normal vector, but how would we actually go about finding one? So you might have the idea, okay, all right, now we can use a parallel vector. So here's another vector. He's parallel to the plane. He's in the same plane, right? All I need to do is make sure that my vector is perpendicular to that vector, right? I'll be able to tell when these two vectors are at 90 degrees because I do have an equation, the cosine equation, that describes the angle between the two vectors. So I can definitely check when one vector is perpendicular to another. However, life isn't that easy. We're in 3 dimensions, not 2. That is also an issue because you see, when I just have 2 vectors, in 2D, yeah, there's nothing else to worry about. In 3D though, there is an infinite number of ways for 2 vectors to be perpendicular, right? Like I can go all the way around this guy at a perpendicular angle. They're all perpendicular. So if I have one vector in the plane and I can find a vector perpendicular to that one, it turns out it's not good enough because, hey, look at that. Here's another vector in the same plane that's perpendicular to the other one, right? It's possible to find multiple vectors that are perpendicular to this vector that's in my plane already. So having a vector in your plane is not good enough to figure out some other vector that's perpendicular to it. So one vector is not enough. Two vectors is. Somehow, all we need is two. You just need one more, right? Now, here's the idea. Let's say I have two vectors in the plane. They don't have to be parallel, right? There can be in two different directions. Here is the goal. If I could find a vector that is perpendicular to both of them at the same time, then that is going to be the vector that I would want to find, because that would ensure there's only one direction that would fulfill that criteria. You see, with one vector, I can be perpendicular to it in an infinite number of ways. However, if I have two vectors in a plane, then this is no longer true. This guy is perpendicular to both vectors at the same time. If I tilt him at all, I can still be perpendicular to this one, but now I'm no longer perpendicular to that one. The moment I mess up the perpendicular the moment I move in another direction, other than the one that's straight up, it will break the perpendicular relationship between either one of the vectors. If I'm able to maintain a vector that is perpendicular to two vectors at the same time, that vector and those two vectors are in a plane that I care about, I will be able to uniquely describe the direction that that plane is moving in. So here's what we've learned from this whole example of looking at a book. Direction is important. How we would identify direction is with a normal vector. In order to create a normal vector, we need two other vectors to compare it to. It's not good enough to compare it to one other vector. So ultimately what we need to do is we need to be able to find a normal vector, and we need to find a normal vector that is normal to two other vectors. There's going to be the need for that down the road. So that's coming, right? And we're not going to deal with that today, but we'll deal with that in the next section. How do you actually go about finding a vector that's perpendicular to two other vectors at the same time? But hopefully now that kind of convinced you as to why this would be important, right? You can't really talk about slope in the same way as you did in 2D. It doesn't work. So now let's go back. Apparently. Okay, so hopefully that was clear. So the answer to this question is we use a normal vector. And this is a vector perpendicular. By the way, perpendicular, as I mentioned, it works differently in higher dimensions than it works in 2. Perpendicular to the plane. By the way, perpendicular, we refer to this, and I'll talk about it later actually. I'll mention it again. This is referred to as orthogonal or orthogonal in dimensions higher than 2. Okay, and we need to find a vector normal to 2 vectors in the plane. Of course, you could do this with 3, but 3 is more than you need. 2 is enough to accomplish this. Right? So that is going to be another issue. And the next couple of sections that we're going to cover will actually have this idea. So I did do go all the way down. Okay. put this picture here. Let's resize. Okay, so this is the issue. So given the same patch, I know vectors running along it. I need to, and let's say these vectors are A and B that are running along it. I would like a vector that's perpendicular to A and B at the same time. This guy's called a normal vector. So I have my vector A. Is it doing the same thing? This thing is so glitchy. Okay. Let me come out and come back in. Every time I navigate away from one node and then come back, it starts to mess with me. Everyone can see it again, right? So here's my vector A, the same A as before. Here's my vector B, the same B as before. And now one of the goals would be, I would need to find a vector N. This is the quote unquote normal vector. That is going to be important to talk about direction in the same way that we talk about direction like the slope of a line back in 2D. So it needs to be orthogonal. Remember, orthogonal is just another name for perpendicular. It's a higher level of perpendicular. Kind of like how derivative is just a higher form of slope. I need to be orthogonal to both A and B in order to get it orthogonal to the plane. I need to make sure it's orthogonal to two vectors in the plane. Being able to find a vector that's perpendicular to two other vectors is therefore an important thing to be able to do, at least if we want to be able to do calculus. Okay. All right, so now hopefully I've spoken enough about motivation. That this is going to be our motivation. Instead of dissecting intervals, it's going to be important for us to be able to dissect 2D regions. And when you go to higher dimensions, it's going to be important for you to be able to dissect 3D regions and etc. To be able to do that, we'll slice them into 2D objects, patches. These are kind of equivalent to subintervals back in Calc 1. This is a higher dimensional analog of that. In order to do that, we need to be able to talk about the area of the patch, what direction it's slanted in, what angle is in the corner, the angle between the two vectors along that thing. All of these things are going to be important. And these reasons are why we need things like a dot product, things like a cross product. That's where they're going to come in. So that's kind of the motivation, to be able to navigate this new environment that we find ourselves in, and to be able to do the kinds of things that we did in calculus. We need a way to talk about all this stuff. How do we need to develop the math that's going to get all this stuff to work? That is our goal. And we're going to tackle one of those goals right now in this section. In fact, we're going to tackle this goal, the goal that talks about finding the angle between vectors. Let's actually do that. Once I know how to do that, I'll know how to measure angles between two vectors at a time and etc. And then I'll be able to figure out from this also areas and all that good stuff. So let's actually deal with that. This leads us to an object, a mathematical object or idea called the dot product. Okay, so now let's actually build this product up. Where does a dot product come from? So I could just start and give you the definition, but let me actually show you how the definition would naturally arise. Sip on my tea here. So let's say I want to find the angle between these two vectors, A and B, and we're in R2 here, we're in 2D, right? So what I show you in 2D, the calculations for 3D and higher will be very, very similar. Okay, so I'm going to extrapolate to higher dimensions later on, but it should be clear to you how it's going to be similar. We saw we could actually figure out the angle between them, and by the angle between them, we of course mean the smaller angle, right? So we can have two vectors. I didn't want to draw it like that, I think. We can have an angle here, and then there's a bigger angle here. Right, so this is a big angle, and this is a smaller angle. We want this one. The angle that we're after, we identify to be the smaller angle. That way we can bound it between something like 0 and pi, and so we know that our trig functions are going to behave in predictable ways, and we won't have to worry about reference angles and all that good stuff. Okay, so earlier we saw that the magnitude of a minus b squared is equal to the magnitude of a squared plus the magnitude of b squared minus 2 times the magnitude of a magnitude of b cosine theta. This we got from the law of cosines, which we all, of course, remember. Let's actually plug in what these guys would look like for the two-dimensional case specifically. This is going to look like the magnitude of a1 minus b1, comma, a2 minus b2 squared, magnitude of a1, a2 squared, magnitude of b1, b2 squared, minus 2. I'm going to leave these in magnitude form because you'll see why it's going to be more convenient. What would these guys actually look like? Well, this is the square root of the sum of the squares of the components. So this is just a1 minus b1 squared plus a2 minus b2 squared equals a1 squared plus a2 squared plus b1 squared plus b2 squared minus 2ab cosine theta. Expanding, this would mean that a1 squared minus 2a1b1 plus b1 squared plus a2 squared 2a2b2 plus b2 squared minus a1 squared minus a2 squared minus b1 squared minus b2 squared equals minus 2ab cosine theta. Now you're going to realize that some of these guys are going to cancel out. a1 squared minus a1 squared, a2 squared minus a2 squared, b1 squared minus b2 squared, b2 squared minus b2 squared. And in fact, 2 is going to be a common term. I can divide those out, divide by 2, divide by 2, divide both sides by 2. In fact, let's divide, you can divide both sides by negative 2. And what do you see end up happening here? Here I have a1 b1 plus a2 b2 divided by the magnitude of a, magnitude of b, and that is going to give me the cosine of the angle. Now here's where you see a common theme that would continually arise. If I were to do this in any dimension, the final result is going to look very similar to this part. The difference is this part is going to be slightly different. But even that, it's going to be very predictable. Something like this is always going to show up. In fact, in n dimensions, it'll just be a longer product. It'll be a1, b1, plus it goes dot, 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 all the way up to an, bn. Essentially, you will have an expression, and what that expression is going to look like, it is going to look like the product of the corresponding components of the vectors added together. Because this expression is very important, and it shows up in this very important application, what we realize that, hey, let's give that guy a name, right? That's what math people like to do. We call this expression the dot product. Of the vector A and B, right? So that's what it's called. And the dot comes from the notation, right? So that leads us here to the notation. So a lot of people just start, oh, this is a dot product. They tell you this. But this is where it comes from. And why would anyone do this calculation? Well, I explained it earlier. We needed to figure out area. That's why we even did this calculation. In doing this calculation, we realized that there's this sort of expression that always shows up. Let's give it a name because it's going to show up in any dimension. Every dimension is going to have an analogous expression like this when we start measuring angles between vectors in that space. So given two vectors, a1 comma blah blah all the way up to an, b1 comma blah 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 all the way up to bn, this expression is called its dot product, and we denote it by a dot b. You literally call it a dot b equals this. You just take a1 times b1, a2 times b2, a3 times b3, all the way up to an times bn, add them all together. This gives you some number. That number is going to be used in finding the angle between the two vectors, but it's an important number in its own right. Here's another thing that we can get right away from this number. We saw earlier that, well, this is just me just re-saying. If you go here and you plug in a dot b, you would get this formula. I do want to also mention the dot product is a scalar. Now, me writing this in all caps in red underlined with a bunch of exclamation points, I understand that that might seem a little bit aggressive, but of course, I want you guys to appreciate I've been teaching math a long time and I've seen almost every mistake in the book. Occasionally, students do things that I've never thought or never seen done, but for the most part, I've seen every mistake in the book. And this is one that shows up a lot, and it is, in the grand scheme of things, a very silly mistake to make. A dot product is a scalar. The result of a dot product is a scalar. Yes, we use two vectors to create it, but the output, the result, is a scalar. A dot product combines two vectors, and the output is a scalar. Specifically this scalar, the product of the corresponding components added together. This is a dot product. It is a scalar, not a vector, to be specific. Dot product is a scalar. Now, okay, so you're gonna say that to yourself 3 times. You go to bed, 3 times when you wake up. Say it like Beetlejuice, it'll keep all the scary monsters away. Dot product is scary, dot product is scary, dot product is scary. Okay. On top of that, there are certain properties that we can prove. With this definition, we can prove the arithmetic with these guys will actually work out in this way. So I'll leave that up here for you to use. And yes, this, I just took this as a screenshot from a book. It says a 3-dimensional space here specifically, but this works in n-dimensional space in general. These calculations will always be true. Now, let's talk about the orthogonal thing, because remember that was important. We learned earlier that being able to figure out when things are perpendicular, quote unquote, orthogonal, is going to be an important thing. It turns out that the dot product gives us a criteria for which this is true. Orthogonal means the angle between the two vectors is pi over 2 radians, which means I can go to this equation up here. I can plug in pi over 2 for theta. Cosine of pi over 2 is going to be what? Well, it's going to be 0. You guys took a long time answering that. You should like immediately answer somebody. Okay, so essentially what we found that is if the angle between the two vectors is pi over 2 radians, the dot product will give you 0. Well, hopefully you said it in your head, Ash. I'm going to trust you that you said it in your head correctly. The dot product is 0 whenever two vectors are orthogonal. In fact, you can take this as an if and only if kind of a theorem kind of thing. A and B are orthogonal if the dot product is 0. So we saw earlier that knowing that one vector is perpendicular to two other vectors is going to be important. How would you know that they're perpendicular? Well, one way to know is to take a dot product. If you take the dot product and you get the answer 0, then yes, they are perpendicular, right? This probably also indicates a way that you could find the perpendicular vector that I mentioned before earlier, right? Just make sure that I set up a dot product with all between n and a, and set up another dot product between n and b, set that equal to 0, and solve for the coordinates of n that will cause that to happen. But we're getting ahead of ourselves there. So we can check that two things are orthogonal, two vectors are orthogonal if their dot product is 0. So that's all we want to do. Two vectors of the same dimension, if the dot product is 0, is orthogonal. And that's now just a thing we know, right? In the same way that we know, okay, two straight lines of the same slope are parallel. If you have a line where the slope is m and it's non-zero, then a line perpendicular to that will have slope -1/m, right? The negative reciprocal. So this is a new mantra that we have now for the higher dimensional case. You should just know perpendicular means dot product is 0. Orthogonal means dot product is 0. That's what it means. Perpendicular in 2D meant the slope, the product of the slopes was -1. In 3D and higher, and even in 2D also, in all dimensions, perpendicular means dot product is 0. That's what it means. The dot product is a 0 scalar means we have perpendicular in 2 directions. We have orthogonal in all other directions. Okay. Parallel, I just recopied what parallel means here. One vector is a constant multiple of the other. Okay. So, I had a comment here about why we call it a new name. So yeah, orthogonal means perpendicular. You'll get into the habit of calling it perpendicular for a while because that's what most of you are used to. Don't sweat it too much, but eventually you do want to use the word orthogonal more. It's the more general term, right? Because perpendicular kind of gives you has the connotation of there's only one other thing, right? If the slope is m, then the other slope must be -1/m as long as it's non-vertical, right? So as long as it's non-zero or non-vertical. So in the same way, these are just new terminologies now. All right, so that is an intro to the dot product, and now you know why it would be important. Right now, let's actually do some math examples. Let's actually do some calculations here. So here's the first example we're going to do. Here I'm giving you two vectors. Compute the dot product, and then find the smallest angle between these two vectors. Okay, so this might be a question that you would have to answer. So let's actually work through this. Okay, so here I know my A, so this is, I didn't number the examples. This is example 1. My A is 1, 2, 3. My B is 1, 0, -2. Then if I take A dot B, you write it A dot B. And by the way, writing the dot, it's important to write the dot. Writing two vectors beside each other does not make sense. It is called a dot product after all. You have to write the dot. It's wrong if you don't write it. Okay, that being said, A dot B would just mean you don't have to write this, but you could write 1, 2, 3 dot 1, 0, -2. But all this is just corresponding components multiplied and then add them together. So this would be 1 times 1 plus 2 times 0 plus 3 times -2. That's 1 minus 6. This is -5, right? Now there's an interpretation that you can have with this -5, but for us, you can think of it as just indicating that's the thing I would have to plug into that equation in order to find the cosine of the angle and hence the angle itself. So a dot product can give you various scalars, but for now, and even in Calc 3, we're never going to be concerned too much with what the magnitude of that scalar is unless we actually want to find the specific angle. But the scalar that's going to be important to us is the 0 scalar. Whenever the dot product is 0, that actually indicates something very important. That indicates that the two vectors in the dot product are actually orthogonal. They are perpendicular to each other. Okay. Now in this problem, we do ask for the angle between them. Find the smaller angle between them. Okay, so I want the angle between A and B. So here I just use that formula. We know that A dot B is equal to magnitude of A, magnitude of B, cosine theta. How do we know that? Jhevon wrote it down earlier. That's a theorem. That's the guy here. Right? So these things in a box obviously have to be memorized. And so A dot B, we just found that. And magnitude of A, well, that's going to be the square root. Is that rad 14? Yeah, we saw that already. Magnitude of B is radical 5 cosine theta. So if I want to actually find the theta, then this just means that my theta is going to be cosine inverse of minus 5 divided by rad 14, rad 5. And that's actually your answer. If you care about what that actually is, I don't know, let me. Professor Wolfram, what is this? So if you look at arc cosine of minus 5 divided by the square root of 14 times 5, close parentheses, close parentheses. This is 2.21 radians. Yep. Of course, you won't be allowed to use a calculator on an exam, so you can leave your answer as the cosine inverse form. Okay, and that's our first problem. Let's do another one. Here's another example. Show that this vector and that vector are orthogonal. So to show that those two vectors are orthogonal, this means you're given two vectors, you want to check if they're actually if they actually meet at right angles. All you're going to do so someone asked a question here. Yeah, if there was a larger angle, you would just take 2 pi minus that. But we normally want the smallest possible angle between the two vectors. It's going to be, we normally want an answer between 0 and pi. I mentioned that somewhere up here, yeah. It's just customary to use that angle. I mean, there are really an infinite number of ways you can write about the angle between two vectors, but we customarily take the one that's between 0 and pi. And the law of cosines is actually going to give us that right away. Okay, so to check something is orthogonal, how do you know something is orthogonal? Dot product is 0. So this means 1, 3, 5, dot minus 5, 0, 1. Well, that's going to be 1 times minus 5 plus 3 times 0 plus 5 times 1. That's minus 5 plus 5. That's 0. This means yes, they are orthogonal. Another example. Find the dot product if we know the magnitude of A, the magnitude of B, and the angle. Of course, that's, again, that's actually using the same formula. We know that A dot B is equal to A, B, cosine theta. This is 2 times 3 cosine pi over 4. And what's cosine pi over 4? I'm waiting on Ash with his slow hands. Rad 2 over 2. So the 2's would cancel. So we get 3 rad 2. And that's the value of the dot product here. Now, don't worry about what that interprets as. All we know, for example, is that these 2 vectors that would have these magnitudes and have that angle between them, it's not perpendicular, which obviously it has an angle of pi over 4 between them. Here is another example. Yeah, tell your brother next time he distracts you, he has to sit in the class. Okay, so suppose a vector is, you have a 2D vector where neither of these guys are 0. Find a non-zero vector B orthogonal to A. Saw this in the textbook. I think there's a very cute answer for it. It turns out B equals, you can swap the 2 entries and make one of them negative. And of course, this can be itself plus or minus. Right? It just says find a vector. So I just, that's the easiest answer probably. Of course, notice that what you would want is you'd want A dot B to be 0. So this would mean A1 B1 plus A2 B2 would be 0. But I can get that by, if I make this guy minus, if I make this guy minus A2, and I make this guy A1, then I end up with A1 times minus A2 plus A2 times A1. That would give me the 0. Right? So that's just a cute little problem there. It's on the textbook. I don't remember where. Don't remember if it was this textbook. Some other things. Now, this is just one final thing we're going to talk about here. Now, this is the idea of projections, which are very, very important. They're important in an application sense. So there are a lot of physics applications for projections. Just trying to not waste space here. Oh, right. Okay, vector and scalar projection. This is going to be important. Very important in physics, very important in engineering, very important in geometry and linear algebra of any kind. There's so many applications to this thing, it's not even funny. We're not going to do any applications though. We just want you guys to actually know how to go about computing them. So I'm going to explain to you what these guys are, maybe explain a little bit about these formulas, do this as an example, and we are out of here. And that would be it for us with the dot product. So sometimes you have 2 vectors, say a vector A and a vector B. And what we would like to do is project a shadow, like pretend we're shining a light from above and project one vector onto the other vector. So I want to project the vector B perpendicular down to hit the vector A. Now, this new vector, this red vector that's created, that vector that lives in the shadow of B, this vector is called the vector projection of B onto A. And its notation is PROJ sub A of B, right? Projection of B onto A, right? So that's the vector projection. Now, if you look at the length of this shadow, like the length of that red line, just as a magnitude, you can use trig to figure out that it's going to be the magnitude of B cosine theta. This is called the scalar projection because it's a scalar, it's a magnitude. And in fact, we have a nice way to actually rewrite this. If we look at B cosine theta, well, that is the same as I can multiply and divide by the magnitude of A. And this guy over here is just your dot product. So this guy is actually equal to A dot B divided by the magnitude of A. Divided by the magnitude of A. And that's the formula that you'll see here. A dot B divided by the magnitude of A. Okay, so that's where that formula comes from. So that's the scalar projection. That's the length of the shadow. Now, if I want to find this vector, here's what we're going to do. I need this vector to have the length of this scalar. So what I want to do, here's how a unit vector is going to come in handy. Find a unit vector in this direction, and then multiply it by this particular scalar, and that will create a vector in this direction of this particular length. So that's what we're going to do. So we're going to take this as a scalar, because it is, dot product is a scalar, and we're going to multiply it by the unit vector in the direction of A. That's this guy here. Of course, that will simplify into this by just taking the magnitude of A and moving it underneath. But that here, this is going to be a vector quantity because in front here is a scalar quantity. A dot B over the absolute value of A squared is scalar. So this is just a scalar multiple of A. In fact, it is the multiple that's going to get this red vector to have this length. Okay, so that's how these formulas actually work out. So that's the vector and scalar projection. Sometimes we want to project one vector onto another. This is very useful in finding distance formulas and equations of different kinds of surfaces in 3D and many other things, okay? That being said, let's just actually know how to use them. You should know these formulas. And of course, I think it's nice to actually build it up from this idea. You can start with a scalar projection and then just multiply that by the unit vector in direction A to get the vector projection. So it's very natural, I think, to actually develop these formulas once you really understand what they are. So I want to project B onto A. So I want to find the component of B onto A. This is this scalar projection. Well, this is just going to be A dot B divided by the magnitude of A. That's going to be 3, 0, 1, dot product 1 minus 1, 2, over the magnitude of the A, which is 3 squared plus 0 squared plus 1 squared. So this is going to be 3 plus 2 over radical 10, looks like. So this is 5 over radical 10. That is the scalar projection. Now I can talk about what's called the vector projection. That's like me taking that scalar and multiplying it by, let's not do that. Let's not put a dot. Dot means something for us now, means something very specific. Multiply that by the unit vector in the direction of A. So that is going to be 5 over radical 10 times the vector 3, 0, 1 over radical 10. In other words, that's going to be a half 3, 0, 1. Or in other words, 3 over 2, 0, 1 over 2. This is the vector projection. So essentially what we had is we have our vector A doing its thing, and then we had our vector B doing its thing, and I actually project a shadow from B down to A, and I create this other vector. Now that vector is going to have, it's going to be the vector 3, 2, 0, 1 over 2. And its length is going to be 5 over radical 10. And those are our vector and scalar projections. And that, ladies and gentlemen, is the dot product. So in 3 dimensions, there's a bunch of things that we're going to want to be able to do with vectors and patches and planes. And knowing how to find angles and areas and perpendicular vectors are going to be important. The dot product helps us with a lot of that. It helps us with the angle idea. And it's this expression. And it comes from actually computing using the law of cosines when we want to find the angle. The dot product is a scalar. It obeys these rules. Dot product is 0 means it's perpendicular, or in higher dimensions, we call that orthogonal. Did a few examples of just doing some computations here. And this is an application of the dot product. It's finding vectors and scalar projections, but they themselves have a lot of applications in a lot of other spheres. So that being said, we will stop there today. I hope today's lecture was insightful and somewhat enjoyable. It took forever to actually make this thing, but I had a lot of fun making it. Next time on Thursday, we will go with the other guy, the cross product, the guy that's going to help us find those perpendicular vectors. A lot of cool stuff coming up. I will see you guys on Thursday and we'll talk about that. But that was the dot product. As usual, I'll share this PDF with everybody. And yeah, so unless there are any parting questions, we're going to wrap up there today. Okay, all right, they're good. All right, well, bye everybody, take care. I usually don't send the PDF in email. I put them at the bottom of the videos. So when I post the videos in the lecture series, it's in the description. Yeah, the link to all the notes for each video is in the description of the video itself. So I link you directly to the PDF version of this. But again, it's just for your reference. You should be taking your own notes, but I understand that I have a lot of stuff typed it and I'm just scrolling. It's hard to take your notes in real time. But you do want to actually summarize, make sure you understand everything. But I will post a PDF of this guy for your reference. That being said, goodbye everybody, take care.